Preparing for an AI security engineer interview. You've reached Interview Guide, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What makes AI security different from traditional application security? AI security protects systems where models influence decisions, code, or user interactions. I separate risks into traditional controls, like identity and network security, and AI-specific risks, like prompt injection, poisoning, model theft, hallucinated actions, and sensitive data leakage. The key is not treating the model as magic. I secure the full pipeline: data collection, training, deployment, inference, monitoring, and incident response, because attackers usually exploit the weakest boundary. While answering, focus on how AI expands the attack surface: data, models, prompts, tools, infrastructure, and outputs. Mention classic security still applies, but probabilistic behavior creates new failure modes. Question 2. How would you threat model an LLM-powered application? I start by mapping the architecture: users, front-end, API, orchestrator, model, vector database, tools, logs, and third-party services. Then I identify assets such as credentials, private documents, prompts, embeddings, and decisions. For each trust boundary, I ask what can be spoofed, tampered with, leaked, or abused. In LLM systems, I pay special attention to indirect prompt injection, excessive agency, insecure tool calls, and data exfiltration paths. Make sure to cover assets, trust boundaries, data flows, model inputs and outputs, external tools, plugins, users, and abuse cases. Mention Stride, OWASP LLM Top 10, and mitigation prioritization. Question 3. What is prompt injection, and how would you defend against it? Prompt injection is when a user or external content manipulates the model into ignoring intended instructions. A direct attack appears in the chat. An indirect attack hides and retrieves documents, emails, or web pages. I do not rely on prompt wording alone. I isolate untrusted content, restrict tools with least privilege, validate structured outputs, use allow-listed actions, monitor suspicious intent, and require confirmation for sensitive operations. In your answer, talk about direct versus indirect prompt injection, why instruction hierarchy matters, and layered defenses like input isolation, output validation, least privilege, allow lists, and human review. Question 4. How would you secure a RAG system that retrieves private enterprise documents? A RAG system fails securely only if retrieval respects the same authorization rules as the source system. I enforce document-level access before retrieval, not just after generation. I isolate tenants, encrypt vector stores, scrub sensitive metadata, and log which chunks influenced each answer. Retrieve text is untrusted input, so I separate it from system instructions and constrain the model's actions. I also test for cross-user leakage using adversarial queries. Be sure to mention document-level authorization, tenant isolation, secure chunking, embedding storage, prompt injection in retrieved content, audit logs, encryption, freshness, and preventing cross-user data leakage. Question 5. What is data poisoning in machine learning, and how can it be mitigated? Data poisoning means an attacker manipulates training or fine-tuning data to change model behavior. The goal may be broad degradation or a hidden backdoor triggered by specific inputs. I reduce risk by validating data sources, tracking provenance, reviewing labels, detecting outliers, and versioning datasets. For high-risk models, I run backdoor tests and compare behavior across clean validation sets. Prevention matters because poison behavior can be hard to remove after deployment. While answering, cover training data integrity, label manipulation, backdoor examples, source validation, anomaly detection, dataset versioning, provenance tracking, robust training, and post-training evaluation against targeted triggers. Question 6. How do adversarial examples affect AI systems, and what defenses are practical? Adversarial examples are inputs crafted to cause incorrect model predictions while looking normal to humans. In vision, tiny pixel changes can flip a classifier. In text, subtle phrasing can bypass moderation. Practical defenses include adversarial training, input normalization, confidence thresholds, ensembles, and fallback review for high-impact decisions. I avoid claiming any single defense is complete. The mature approach is risk reduction, continuous testing, and designing safe failure modes. Make sure to cover small input perturbations, model brittleness, computer vision and NLP examples, adversarial training, input preprocessing, confidence thresholds, ensemble methods, monitoring, and defense limitations. Question 7. How would you protect a proprietary model from extraction or inversion attacks? Model extraction happens when attackers query an API enough to approximate the model or steal decision boundaries. Inversion and membership attacks try to infer training data or whether a record was used. I defend with rate limits, authentication, usage monitoring, response throttling, reduced confidence scores, and anomaly detection for probing patterns. For sensitive training data, I consider differential privacy and data minimization. Business controls also matter: contracts, watermarking, and abuse enforcement. In your answer, discuss model extraction through repeated queries, membership inference, training data reconstruction, rate limits, output restriction, watermarking, anomaly detection, differential privacy, and legal or contractual controls. Question 8. What security controls would you apply to an ML supply chain? An ML supply chain includes code, dependencies, datasets, notebooks, models, containers, and deployment pipelines. I treat model artifacts like production binaries. That means signed artifacts, trusted registries, dependency scanning, pinned versions, SBOMs, and reproducible training where possible. I restrict who can modify datasets or training jobs, scan containers, and prevent secrets from entering notebooks or logs. The goal is traceability, knowing exactly what produced the deployed model. Be sure to mention dependency pinning, model artifact signing, dataset provenance, CI/CD scanning, container hardening, reproducible builds, registry controls, SBOMs, secrets management, and access control for training infrastructure. Question 9. How do you evaluate whether AI guardrails are actually working? I evaluate guardrails like security controls, not slogans. First, I define prohibited behaviors and acceptable error rates. Then I build test sets for jailbreaks, data leaks, unsafe tool calls, toxic output, and business policy violations. I measure both bypass rate and false positive rate because overblocking hurts usability. Before full rollout, I use canaries and production telemetry. Guardrails need regression testing whenever prompts, models, tools, or retrieval sources change. While answering, focus on measurable safety tests, jailbreak suites, policy violation rates, false positives, regression tests, red team prompts, canary deployments, production telemetry, and feedback loops. Question 10. How would you prevent sensitive data leakage in an AI chatbot? I address leakage at input, retrieval, generation, and logging layers. Inputs should be classified, redacted where appropriate, and blocked from training unless users explicitly consent. Retrieval must enforce authorization before documents reach the model. Outputs need checks for PII, secrets, and policy violations. Logs are especially risky, so I minimize them, encrypt them, and apply retention limits. A chatbot should never become a shadow database of sensitive conversations. Make sure to cover PII detection, data classification, prompt and response logging, redaction, access control, retention policies, secure retrieval, training data exclusions, and user consent. Question 11. How would you design access control for a multi-tenant AI platform? For a multi-tenant AI platform, I start with hard tenant isolation in storage, metadata, embeddings, and logs. I use RBAC for roles and ABAC for context, such as project, data sensitivity, and environment. API keys should be scoped, rotated, and tied to quotas. Users need separate permissions for datasets, models, fine-tuning jobs, and deployment endpoints. I also test for cross-tenant leakage through retrieval, caching, prompt history, and analytics pipelines. In your answer, talk about tenant isolation, RBAC and ABAC, scoped API keys, model and dataset permissions, audit trails, encryption boundaries, quota controls, and prevention of cross-tenant inference leakage. Question 12. What would you monitor in production for AI security abuse? I monitor both classic application signals and AI-specific behavior. Classic signals include authentication failures, rate spikes, anomalous geographies, and privilege changes. AI signals include repeated jailbreak attempts, prompt fuzzing, high-volume probing, unusual vector searches, tool call failures, and outputs flagged for sensitive data. Cost and latency spikes can also indicate abuse. The important part is context-rich alerting, so responders can see user, prompt, retrieval, tool, and output events together. Be sure to mention prompt patterns, excessive querying, jailbreak attempts, tool misuse, unusual retrieval behavior, data exfiltration indicators, latency or cost spikes, model drift, and alert triage. Question 13. How would you red team an AI assistant before launch? I red team from realistic attacker goals, not random prompts. For an AI assistant, I test jailbreaks, prompt leakage, sensitive data extraction, policy bypass, malicious file content, and unsafe tool execution. I include multilingual and encoded attacks because filters often miss them. Each finding gets severity, reproduction steps, affected controls, and recommended fixes. After remediation, I rerun the same cases as regression tests, then keep a smaller suite in CI. While answering, cover adversarial prompt design, abuse scenarios, role-play attacks, indirect injection, data leakage, unsafe tool use, multilingual attacks, scoring criteria, documentation, and remediation tracking. Question 14. What security risks come with fine-tuning a model on internal company data? Fine-tuning can improve domain performance, but it can also memorize sensitive internal data or learn poisoned behavior. I would minimize the dataset, remove secrets and unnecessary PII, validate provenance, and separate training from evaluation data. Access to the fine-tuned model should match the sensitivity of the data used. After training, I test whether the model regurgitates confidential snippets. If risk is high, RAG with strict authorization may be safer. Make sure to cover memorization, poisoned examples, permission boundaries, data minimization, consent, evaluation data separation, model access control, rollback, and checking whether sensitive content can be regurgitated. Question 15. How do output filters differ from model alignment, and when would you use each? Model alignment shapes the model's default behavior. Output filtering checks what leaves the system. Alignment helps reduce unsafe generations at the source, but it is imperfect and can regress across model versions. Output filters provide an independent enforcement layer for PII, toxicity, secrets, or policy violations. I use both, aligned models for better baseline behavior and filters for explicit policy boundaries. The trade-off is latency and false positives, so measurement is essential. In your answer, discuss pre-generation versus post-generation controls, policy enforcement, false positives, bypass risk, defense in depth, model behavior shaping, and why neither approach alone is sufficient. Question 16. How would you secure tool calling or agentic workflows in an LLM application? Tool calling is where LLM risk becomes operational risk. I never let the model execute arbitrary actions directly. Tools should have narrow scopes, structured inputs, validation, authorization checks, and audit logs. Destructive or financial actions need explicit user confirmation and transaction limits. I sandbox code execution and block network or file system access unless required. The model can propose actions, but deterministic services must enforce policy before anything real happens. Be sure to mention least privilege, tool allow lists, structured schemas, user confirmation, sandboxing, transaction limits, audit logs, deterministic validation, and preventing the model from directly controlling sensitive actions. Question 17. How would you respond if an AI system leaked confidential data in production? I would treat it as a security incident, not a model quality bug. First, contain exposure by disabling the affected feature, revoking access, or rolling back prompts, retrieval indexes, or model versions. Then I preserve logs and identify who saw what data. I investigate whether the leak came from training memorization, RAG authorization failure, logs, or prompt injection. Finally, I coordinate legal, notify affected parties if required, and add regression tests before re-enabling. While answering, cover incident triage, containment, log preservation, affected user identification, model and prompt rollback, retrieval source analysis, legal notification, root cause analysis, and prevention of recurrence. Question 18. What compliance and governance concerns matter for AI security engineering? AI governance connects technical controls to legal and business accountability. I care about what data is collected, why it is used, how long it is retained, who can access it, and whether users gave consent. For regulated use cases, I document model purpose, limitations, evaluation results, approval workflows, and audit logs. Vendor models add third-party risk, so contracts and data use terms matter. Good governance makes security decisions reviewable and defensible. Make sure to cover data protection laws, auditability, model risk management, explainability, retention, consent, access logs, vendor risk, policy documentation, and mapping technical controls to regulatory requirements. Question 19. What are the security risks of embeddings and vector databases? Embeddings are not harmless hashes. They can reveal semantic information about the original content. A vector database may expose sensitive relationships through similarity search, metadata, or cross-tenant retrieval bugs. I secure it with tenant isolation, encryption, strict access control, metadata minimization, and authorization checks before returning chunks. I also plan deletion and re-indexing workflows because removing source documents is not enough if derived vectors remain accessible. In your answer, talk about embedding leakage, semantic inference, unauthorized similarity search, tenant isolation, metadata exposure, deletion challenges, encryption, access control, poisoning, and secure index lifecycle management. Question 20. What metrics would you use to measure the maturity of an AI security program? I measure AI security with outcome and coverage metrics. Coverage includes how many AI systems have threat models, data inventories, access reviews, red team tests, and secure release gates. Outcome metrics include jailbreak bypass rate, sensitive data leakage rate, unresolved high-severity findings, incident frequency, and mean time to remediate. I also track supply chain controls like signed model artifacts and dataset provenance. The best metrics drive action, not just dashboards. Be sure to mention coverage of threat models, red team findings, guardrail bypass rates, mean time to remediate, sensitive data leakage tests, supply chain controls, incident trends, and secure release gates. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.